Well, this is the last lecture, so I thought what I would do is I would outline the classification of semisimple algebraic groups. I'll do this over an algebraically closed field of any possibly positive characteristic. Okay, so I think it's kind of nice to come back to algebraic groups at the end here. So maybe I should remind you what semisimple algebraic group means. That's a connected algebraic group G with no connected closed normal solvable subgroups. That is the subject with lots of adjectives, so there we go. So that's semisimple algebraic group, and well, I guess, you know, I'm going to be a little bit sketchy. I'm not trying to prove anything. I'm just trying to give you this glimpse of this kind of wonderful next topic that you might read about in Springer's book, for example. There's actually a more beautiful way to formulate this, where you don't work with semi-simple algebraic groups, you work with reductive algebraic groups, and the result's much more pleasing in that form. But I'm just going to formulate it in this kind of slightly cheap and dirty way for just semi-simple algebraic groups. Let me see. So over the complex numbers, G is a semi-simple algebraic group, if and only if its Lie algebra is a semisimple Lie algebra. That's something we talked about back in week 4, I think. And so in this case, we see that there's a root system. In the background. But even in this case, the classification of the groups needs more data than that. I mean, we already see this, right? Because, for example, you have SL2 and PSL2. They're non-isomorphic algebraic groups, but they both have the same Lie algebras, little SL2 of C. So there's got to be some additional data. Okay, so let's talk about that additional data just a little bit. So let's let R sitting inside E be a root system. And let's do our usual business with root systems. Let's pick a base, alpha 1 through alpha L. And perhaps you remember that we had Q and P, the root lattice and the weight lattice, defined before. So Q was the free abelian group generated by the alpha i's sitting inside that Euclidean space E. So that's a free abelian group of rank L. And P, those were the weights. So that was the free abelian group generated actually by the fundamental weights, these pi i's. That's another free abelian group of rank L. So maybe I should remind you a little bit of this. So the pi i's, they were the dual basis to the co-roots. So if you want to write the ith simple root as a linear combination of the fundamental weights, should be able to do that, right? Because the root lattice sits inside the weight lattice. What are theCij's? Well, to work out Cij, all you have to do is take the inner product with, to pick out this coefficient, if I take the inner product with alpha j check, that will pick out Cij, right? So Cij is alpha I, alpha j check. Oh, this is the Cartan integer. In fact, C, this matrix of these Cij's is the Cartan matrix. So what we have here is we've got two free abelian groups of rank L, Q sitting inside P, and the Cartan matrix is the transition matrix between a basis for P and a basis for Q. So in particular, that means that P over Q, this is a finite abelian group of order, well, that order will be the determinant of the Cartan matrix. In fact, you could calculate exactly which finite abelian group this is by you have to find the elementary divisors. Of C. So this group P over Q is called the fundamental group of the root system. So it's very computable from each of the Dinkin diagrams. You can work out the fundamental group quite easily in terms of the Cartan matrix. An isomorphism between two root systems, in the sense that we defined it, well, it takes the root lattice to the root lattice and the weight lattice to the weight lattice, so it induces an isomorphism between the fundamental groups. Okay, so that's kind of a basic invariant of a root system up to isomorphism. So now I think I can state the theorem. Remember, this is a sort of somewhat cheap and dirty way of saying things. But I want to say it so that you see it in parallel with the classification of finite dimensional semisimple Lie algebras that we've given. So there's a bijection from semisimple algebraic groups. And the remarkable thing is this is over any algebraically closed field, viewed up to isomorphism, and pairs Re gamma consisting of a root system and a subgroup of its fundamental group. And so the root system comes with this fundamental group P over Q. Gamma is just a subgroup of that finite group. Taken again up to isomorphism of root systems, at which an isomorphism of root systems induces an isomorphism from gamma to gamma prime, right? So isomorphisms of the root system respecting that subgroup of the fundamental group. That's what I mean there. Okay, so there's the theorem. Great. That's kind of it doesn't say very much the way I've stated it because I haven't given you exactly what the map is. So let me see if I can do that. Actually, before I do that, let me give you some examples. So this is a theorem without a whole lot of meaning, without expanding actually what the bijection is, but I'll do that in a little bit. Let's just give some examples to just get the hang of that statement. So first of all, let's think about the root system A3. So that would be the simple Lie algebra SL4 of C. So the Cartan matrix for that is that Cartan matrix. And, well, it's easy to see that the determinant of that Cartan matrix is 4. In fact, the fundamental group, in this case, is the cyclic group C4. That's a little bit more calculation. You have to actually calculate the elementary divisors of that integer matrix. So C4, of course, it has a C2 subgroup and then a trivial subgroup. So we should find that there's 3 different isomorphism types of semisimple algebraic group with Lie algebra SL4 of C. Indeed, well, let's do it over the complex numbers. There's SL4 of C, and there's PSL4 of C, and then there's one in the middle. There's SL4 of C quotiented out by plus or minus the identity. So in fact, over the complex numbers, this is kind of easy. So there's always this one here where the fundamental group is the biggest possible one. So this is called this is the simply connected algebraic group of this type. So this is sort of the universal one, and then all the other ones you get by, so of course the center of a SL4 of C, that's the group of 4th roots of 1. It is indeed isomorphic to our C4 fundamental group. In this case, we're over the complex numbers, and you get the other simple algebraic groups of this type just by factoring out part of the center. So here I factored out the C2 sitting inside that center, and to get PSL4 you factor out the entire center. So this is over the complex numbers, but the same classification works even in characteristic 2, an algebraically closed field of characteristic 2, but you have to be more careful. The simply connected one is SL4 of K, and then this guy is the adjoint group PSL4 of K, which I've showed you how to define. And indeed, the one in the middle, it is a homomorphic image of SL4 of K, but you have to take some representation of that group and take the image under that homomorphism. You can't. The center's trivial in characteristic 2. You can't just factor that out to get the other one. So you actually have to. Well, we talked about that for PSL2 for sure. So there's an example. Even in characteristic 2, there are 3 isomorphism types of simple algebraic group of type A3, corresponding to the 3 subgroups of the fundamental group. Let's do SO8 of C. So this is D4. So the Cartan matrix is something like this, right? So we're looking at D4. There's the Dinkin diagram, and then what do I need? So again, the determinant of C is 4, but when you calculate the fundamental group, you find that it's actually the Klein 4 group. So you actually have 3 C2s sitting inside there. And the corresponding simple algebraic groups, well, corresponding, the simply connected one, when the group gamma is the whole fundamental group, that's the spin group, it's spin 8 of C, and then you have SO8 of C, and then there's PSO8 of C. So again, there are 3 simple algebraic groups of this type. I'm just writing this over the complex numbers, but it's the same story in any characteristic. So something kind of a little bit weird's going on here, right? Because what's going on is that there are actually three different SO8 of C's. There's three different ways, right? So over the complex numbers, the center of spin 8 is still C2 cross C2, and you get three different quotients of spin 8, all isomorphic to SO8, by factoring out different C2s in the center. And those are genuinely different quotient groups of spin 8, but they're all isomorphic. But the isomorphisms come from outer automorphisms of this group, in fact. Out spin 8, group of outer automorphisms of that group. It's actually isomorphic to S3. It's the group of symmetries of the Dynkin diagram. In particular, you have this triality corresponding to the 3 cycle in S3. This is the triality automorphism of spin 8. So I've explained that over the complex numbers, where you can see what's going on by thinking about the center of this algebraic group. But the classification is the same for any field. There are these three non-isomorphic simple algebraic groups of type D4. It's just that it's not good enough to look at the center to distinguish them. And that's kind of one of the miracles of this theorem, right? It works for any algebraically closed field, whereas the theory of semisimple Lie algebras, you're very much tied to an algebraically closed field of characteristic 0 for it to all be nice. For algebraic groups, it just works uniformly over any algebraically closed field. Okay, so I want to try and tell you actually what the isomorphism is. Where does this group gamma come from in particular? It can't just come from looking at the center, because that doesn't work in positive characteristic, even in those examples. So let's explain the forward map in this classification theorem. So that's all I'm going to do. I'm not going to obviously attempt to prove anything here, but I do want to tell you how you construct that map, that bijection. So you start off with your semisimple algebraic group G. You pick T, a maximal torus. So T will be just some product of multiplicative groups. L of them, that'll be the rank of the torus. So again, there's a conjugacy theorem here. All maximal tori of an algebraic group, they're all conjugate. So it doesn't matter which T that you pick for the purposes of defining this map we're going to define, because it's all up to isomorphism. And then you let G be the Lie algebra of G, and T be the Lie algebra of T. And what we're going to do is we're going to consider the adjoint action of T on that Lie algebra. Okay, so this is a torus, so you get a decomposition of that as, well, the Lie algebra of T will be in there, and then it turns out that you get this direct some decomposition of G alphas, which should look awfully familiar, but there's a difference here, because we're now decomposing with respect to this adjoint action of an algebraic torus, rather than this Lie algebra, this maximal toral Lie algebra that we had. So let me write down a few definitions. So you need to take lambda in x of t. So you see this on homework problems. So this is the character group of that torus. So that's morphisms of algebraic groups from the torus to the multiplicative group. This is a free abelian group. It's isomorphic to z to the L. It's a free abelian group of rank L, where L is the rank. That's just the dimension of the torus, that algebraic group. Okay, so so for a character of the torus, a homomorphism from the torus to the multiplicative group, we write G sub lambda for the set of all elements of that Lie algebra such that add T of x is lambda of T x for all T in the torus. Okay, so this is kind of the multiplicative version of the weight spaces that we had for the Lie algebra. It's just that now, instead of weights being elements of our maximal toral subalgebra T star, these weights are characters of the torus. And then R, then that's the set of all non-zero elements lambda in the character group such that G lambda is non-zero. I guess I normally write alpha at this point when I'm talking about roots. Okay, so that's a little bit different than before, but if you're over the complex numbers, well then this T is a maximal toral subalgebra of G. The character group of the algebraic group T embeds into the linear dual of that Lie algebra, and this actually is the Cartan decomposition. As usual, that's exactly what it is in you. But you see, now we're over a field possibly of positive characteristic. We don't want to think in terms of Lie algebras so much. We're thinking in terms of the algebraic group and its maximal torus. And so we're decomposing the Lie algebra as a module over that algebraic group T. But so now we're starting to see the data of a root system appearing. So you see, now we have a set of roots sitting inside x of t, which is a free abelian group. Whereas in the Lie algebra theory that we did before, we had the root system sitting inside T star, where this was a complex vector space. And so what we want to do is we want to now construct a root system. So this is meant to be a real vector space, right? This E is meant to be this Euclidean space. So now what we've got to do is actually we have a free abelian group. So now we've got to extend scalars to get a real vector space, right? So we're this E, it sits in between this free abelian group x of t and the T star that we had before. So in the algebraic group theory, what you have naturally is x of t, this free abelian group, and you get the Euclidean space by extending scalars, whereas in the Lie algebra theory, we had this complex vector space and we had to descend down to a real vector space. So you're sort of seeing the difference in the two theories a little bit here. So we want to make E into a Euclidean space, so we need an inner product. So that this is a root system. So the way this is done is a little bit different. We don't have this killing form naturally around, this bilinear form that we can start with, but what we do have, we have the Weil group. We have our algebraic group, right? So we have groups around straight away. Take the normalizer in the group of the torus T. T is a normal subgroup of that. Take the quotient group. And it turns out that this is a finite group. All of the things I'm writing need to be proved. I mean, even the fact that this decomposition looks the way it does, with T being the zero weight space, and then all these G alphas. These G alphas, they're all one-dimensional. I didn't write that down, but everything needs to be proved starting again from scratch in the setup of algebraic groups rather than in the setup of Lie algebras. So everything needs a kind of completely new groupy proof rather than a Lie algebra proof. So the fact that this group W, normalizer of T over T, is a finite group needs to be proved. Of course, it acts naturally on T by automorphisms, and so it acts naturally on the character group X of T. Hence on this Euclidean space by R linear maps. Okay, so then you just pick a W invariant inner product on E. So you do that. This is a finite group, so this is easy. You pick any inner product on the finite dimensional vector space E, and then you just symmetrize over W to get a W invariant inner product. Okay, so there's choice there, but just as with root systems, that's unique up to a scalar on each irreducible constituent of E viewed as an RW module. And that's good enough because we're trying to get root systems up to isomorphism. And then you show that R sitting inside E, which has now been made into a Euclidean space, is a root system and this group W is exactly its Weyl group. Okay, so lots of work to do that, but that's how this comes about. So now we've almost got everything. We've got the root system. But we still need that finite subgroup, well, that subgroup of the fundamental group. Of this root system. But that's just the character group X of T over Q, so you have to show that Q sits inside the character group sits inside P, so it makes sense just to take that character group of your torus modulo Q, and that's the group W. This then is the map in the theorem. What about the other direction? So in the Lie algebra case, what did we do there? Oh, we took a root system, we wrote down its Cartan matrix, so, and then I gave you the Serre presentation. That was the way we constructed a semisimple Lie algebra out of the root system. It was the Serre presentation. What's the analog of that story for algebraic groups? Well, so let me explain that over the complex numbers. So you take your root system and your subgroup of the fundamental group. We're trying to construct the corresponding group G out of that data. So how do you do it? Well, so the first step is you pick a base, usual game. Hence you get a Cartan matrix C. You get a Lie algebra, complex finite dimensional semisimple Lie algebra, just defined by that Serre presentation, and you get a triangular decomposition of that, corresponding to the choice of base. So you do what we did for semisimple Lie algebras. So far we've got that semisimple Lie algebra. We have this extra little piece of data, gamma, this subgroup of the fundamental group, and we're trying to construct a semisimple algebraic group, G. Well, okay, so now we've got to bring that subgroup of the fundamental group into play. So what we're going to do is we're going to pick a dominant weight so that P of lambda over Q is the given group gamma. Now, here are some things that I haven't really used very much. So remember, this P of lambda, it was the set of weights of the finite dimensional irreducible L of lambda of highest weight lambda. So that was what I talked about in lecture 10.1, the classification of finite dimensional irreducible representations. And I explained how you get these L of lambdas, they're labeled by these dominant weights, and the set of weights of L of lambda, it always lies between the weight lattice and the root lattice. In fact, you can get any intermediate subgroup by picking a suitable dominant weight lambda. Okay, so you pick your lambda so that the weight lattice generated by the irreducible L of lambda modulo Q is exactly the given subgroup of the fundamental group. So in other words, the way this fundamental group comes into this construction, it comes via representation theory. So I'm going to just let V be L of lambda for short. And then I'm going to exponentiate G in the representation. So all you actually have to do is you set xi of t be exp rho of tei. That's our generator in the Sayre presentation, and you let yi of t be exponentiating the fi's. And then you look at the group G, which is generated by all these xi of t's and yi of t's for all complex numbers c and I going from 1 up to L. So that's a closed connected subgroup of GLV, so that produces a connected algebraic group. That's the sort of stuff we were doing in lecture 10.2, and it turns out this is exactly the semisimple group realizing the root system and that subgroup of the fundamental group. And this is in fact the two-sided inverse of the map I told you before. So there's a ton of work going into this. And I've still only constructed a semisimple algebraic group over the complex numbers. What about other fields? So there's more work to be done. In fact, there's more miracles here. So for general fields, what you need are things called Chevalley groups. You need the Chevalley construction of Chevalley groups. So I'm just going to kind of end with this. So what you have to do, you have to pick what's called a Chevalley basis for that complex semisimple Lie algebra G. So this is E alpha indexed by roots together with H1 up to HL. That's a basis for that Lie algebra. And we kind of did this more or less before if you let f alpha be E minus alpha for short, and H alpha be the bracket E alpha F alpha, then those E alpha, H alpha, F alphas are the SL2 triples we always used before. And of course, HI is H alpha I, corresponding to the simple root. So that's the sort of standard basis we were picking before. Chevalley basis is one of those standard bases, but it's normalized between different roots in a better way. So this, the existence of this is a theorem. And the point is you can pick it so that all the Lie algebra structure constants are actually integers. So the main extra point is that you need to know how to bracket E alpha and E beta for alpha and beta that are linearly independent roots. And in a Chevalley basis, these are chosen, well, of course, E alpha, E beta is 0 if alpha plus beta is not a root. But if alpha plus beta is a root, and if you let, I need this alpha string through beta, to define R and Q, then in a Chevalley basis, the Lie bracket of E alpha and E beta, it's always plus or minus R plus 1 E alpha plus beta. And there are some signs to choose carefully, which is somewhat annoying in the story, but not really deep. You've got to always remember these finite dimensional semisimple Lie algebras, they're absolutely explicit objects. They're just vector spaces with an explicit bracket, and you can construct them along with the Chevalley basis. They're totally concrete objects. You can literally get your hands on them. Okay, so you start from a Chevalley basis chosen like that. Let's just assume that gamma is actually the entire fundamental group, i.e. I'm just going to construct the simply connected group G. That's actually enough, because to get any other type, you take homomorphic images of the simply connected one. That's kind of the universal Chevalley group, it's often called. Right, so that's the choice of representation V that we're using. We're assuming that its weights generate the whole fundamental group modulo Q. So then I'm going to let X alpha of T be exponentiating T E alpha, where now this is from the Chevalley basis. And it turns out that this group G that I defined before, I generated it just before with the xi's and yi's that corresponded to the simple roots and their negatives, but it's also generated by all x alpha of t's for all roots. And so the miracle is that the following relations hold. Well, we know lots of these relations already, right? These are these root groups just coming from exponentiating. This is for T and T prime in C. And then the cool relation is the following: x alpha of T, x beta of T prime. So this is for alpha and beta linearly independent. And this is commutator in the sense of groups. So G, H, G inverse, H inverse, the group commutator. And there's an amazing formula for this. It's the product. Okay, I'm running out of room to write this thing. You have to take the product of all I and j greater or equal to 1 such that I alpha plus j beta is a root. And then you get the element of the root, the I alpha plus j beta root group. And then it's something like t to the I, t prime to the j with some cij in front. And this product needs to be taken in some fixed chosen order. It doesn't matter what order you choose. But the Cij's here, these are kind of some nasty constants. These are constants which, depending on, well, obviously I and j, but they also depend on alpha and beta. They depend on the order of that product over I and j. You see, these guys do not commute, so you've got to pick an order here. And they depend on the signs in the choice of Chevalley basis as well. So, but they can all be worked out explicitly. The important thing is that the Cij's are integers. So that's relation 2. There's 2 more relations, and I'm not going to fit them in here. Relation 3 is that sigma alpha of t x alpha of t prime sigma alpha of t inverse is x minus alpha of minus t squared t prime. So now this is for t being a non-zero scalar and t prime being any scalar, where, well, you know what sigma alpha of t is. That's that formula that I was showing you last time. You build it from the root groups, x alpha of t, x minus alpha of minus t inverse, x alpha of t. So that's an element of our group G. And finally, gamma alpha of t, gamma alpha of t prime is gamma alpha of t, t prime. This is for non-zero scalars t and t prime, where now gamma alpha of t, well, that was the diagonal matrix that we were calculating last time. So that was sigma alpha of t, sigma alpha of minus 1. So all those kind of crazy formulas are appearing here. So you check all of those relations, 1, 2, 3, 4. Okay, so this is the wonderful one. This one here is called the Chevalley commutator formula. And they're slightly scary, those scalars Cij, but they're integers. So you make all these choices over the complex numbers, and then you get out this bunch of integers Cij, so that these group commutators in this Chevalley group satisfy this Chevalley commutator formula. Okay, so there's our Chevalley group. It's got its generators, and I've written down relations 1, 2, 3, 4. So now here's the miracle. Well, there's many miracles at this point. These give a complete set of relations for the group G. The relations make sense. With the complex numbers replaced by k. In fact, any field, not even an algebraically closed field, make total sense in the relations just written. And so what you do is you then take this set of relations and you get a group G of k for any field k. This is the universal Chevalley group over K. And so I think this was Chevalley's great achievement to understand that these groups could be defined essentially over the integers. They make sense over any field at all, these relations that have been written down here. In fact, Chevalley had a slightly more elegant construction where he was able to construct these groups G of K by exponentiating, as we've done, not over the complex numbers, but by making sense of exponentiating over any field. And you produce this group G of K dependent on the root system, the subgroup of the fundamental group, and the field K. So over an algebraically closed field, this is precisely the construction of an arbitrary semi-simple algebraic group. But this construction becomes very important even over finite fields, right? You get G of Q's, these finite simple groups. So these are the finite groups of Lie type. And I think that's where we should stop. I mean, you should always end a course by kind of opening the page of a vast new chapter, and this is one particular direction you might go.